Okay. So, getting data into QGIS. Have you used QGIS? Everybody used QGIS? Or at least familiar with it? Yeah. Yeah. Okay. Why QGIS? Well, ArcGIS, you need what's called the Spatial Database Engine to connect to a PostGIS database. We don't, well, we have the license for the SDE. I don't think we have it installed. We don't have it installed on the university network. I believe there are various tricks that can be done with ArcGIS, so it does connect to PostGIS without the Esri extension, which costs lots of money. My brief attempts to try and do it failed dismally, and I gave up. So, hence QGIS, which is actually turning into a very good, serious rival to ArcGIS. I certainly know that a number of councils which used to have, say, 20, 30 ArcMap seat licenses, now maybe have 3 or 4 ArcMap licenses for the, what you could call the super users, and the rest of the councils are running with QGIS, free QGIS licenses, and they use the money from the ArcGIS license money to pay for somebody to look after QGIS, the QGIS system. Far better way of doing things, really. Anyway, so how do we do? Well, there's a button on the left. Oh, no, QGIS, we've got the Postgres elephant button. I don't know why they have an elephant, but they have an elephant. You press plus, you connect to your PostGIS, send in your connections to your PostGIS database, just like you do through pgadmin3, your host, your port, your database, etc. Do your connections. Once you've connected, press the connect button, set up your connection, you connect to the database, you get a dialog, lists the tables that are spatial tables that are available in those databases, shows what data points they're SRIDs. You simply select these and add. Voila. It's only taken us 6 weeks, 6 lectures to get a map, but there we are, we have a map finally. Yeah, make yourselves lucky. I'll give you a map. Okay, so there's my fish on my Mexican rivers with my basins. Okay, not all data is spatial. What about aspatial data? How do we get normal tables into Postgres, into QGIS? Well, this is import. First of all, we have to import, because this is so first of all, let's import a table, a standard table into Postgres, then access that table in QGIS. So here I've got a DBF table, a database format table, a .dbf. You're familiar with .dbf? Shape files. A .dbf is an old school database format, and the attributes, if you look at the various files that make up a shape file, one of them is .dbf, so that is where the attributes are stored for a shape file is in a DBF file. Okay, so we're importing a DBF file called ecology, which has ecological information for the fish species. And notice here, this is in the pgadmin import plugin, that there's a pull down here that makes the DBF files available. I could have imported this as a text. I could have exported the DBF as a text file and then imported it like we've done before, but this is actually directly importing a binary DBF file format. In QGIS, sorry, in the importer, in the options, we need to check load only attribute DBF data. Despite this, we've only selected a DBF file. If you don't check this, then I got an error. I don't think I should have got an error, but I did. But when I checked this load only attribute data, then my DBF, because when you do the add, notice it's got this, it adds it in as a shape file, the fact that it's only a DBF file. So therefore we now have to sort of override that and say it's just a DBF file on the importer. So it's a little clunky, the interface, but not desperately. Okay, then in QGIS, when we want to add a table that doesn't have geometry on the Add PostGIS Tables dialog, you need to check that box at the bottom there that says also list tables with no geometry. And here we go. Here's all the tables that are no geometry. So now we've got, look, we've got basins, which is our geometry table, but it's also listing a copy of that with no geometry as well. So you could load in a version with no geometry or a load version with geometry. There's no point in loading up the geometry if you're not using the geometry. It's just wasting space. Also notice that the views are listed here. So the raster columns, the raster overviews, the geography columns are also listed. So the views are listed, and we'll see that's really useful later on. In this case, I'm going to select the ecology table, which I want to import. And now on the left-hand side at the top there, you can see I've got an ecology table with the tabular data there. I can start joining it to my fish data, for example, if I wanted to do that, which is the most likely thing I would do with it. All right, spatial. So we're now actually going to get into the meat of spatial SQL for probably the remainder of the lecture. So spatial SQL is simple SQL statements that include PostGIS functions in this case that operate on spatial columns. So I hope these are readable. I wish the text might be a bit small. I advise you to sit to the front. Always sit to the front, not the back. It's easier to see. And if you've got my eyesight as bad as mine, you have to sit to the front. Okay, so we get some example queries. So I've got my rivers, linear lines, set of lines. I want to know the length of each line in my river table. So my select statement, I'm selecting the name, which is the field, which is the name of a river. As you notice, only some of the rivers actually have names associated with them. Many of the rivers, I have no idea what they're called. It's only the main channels where I happen to know what the names are. I put the names in. Then I can use the function, the PostGIS function st, so it's an OGC compliant function, underscore length. I input the geometry field that I want to get the length for, geom. They're all called geom in this example. All the geometry fields in all the tables are called geom. So I input the geometry field as length meter, the alias that I'm going to return from river. And I know this is in meters because it's an Lambert conformal conic projection which has a base unit in meters. So I've got no conversions here, and that simply gives me the name and the length of the line. Brilliant, very straightforward. We can get, of course, far more complex. Rivers in my database, there may be more than one section, or we call them river reaches, for each named river. So imagine having, say, the Thames, you've got one line that goes from the estuary, the mouth of the estuary, say, to Tower Bridge, another one from Tower Bridge to the next bridge, something like that. So you've got a whole section of lines, different rows in the database representing that river, okay, rather than having one line for one river. Yep. So I want to know the length of the 6 longest named rivers in my database. So I've got more than one row with the name Leo Lerma, more than one row with the river name Rio Grande de Santiago. Actually, geographically, the Rio Lerma and the Rio Grande de Santiago are actually physically connected to each other, and should in fact be called one river if you're talking rivers, but this is all about names and the complexities of names. So I select my name of my river. Because each named river can be made up of more than one row in the data table, I need to do a sum, just use your standard SQL sum function, on the length of the geometry grouped by the name. Yep. So we're grouping all the geometries by the name field, then summing all the lengths of the lines. I've omitted lines where there is no name, because no name lines are not one river. They're scattered all over the place. There are lots of little rivers in my database which I don't have names for. And then to get an order by, so if we go from the longest river to the shortest river, I've got an order by statement on the sum st length geometry descending. So I use the same function here that I'm returning to do the ordering. I think I tried putting the alias in here and it didn't work. So I don't think you can put aliases in order by functions. You have to actually state the function in entirety. And I put a limit of 6, so I've now got the 6 longest named rivers, which I've summed from their component parts. So that's an example of an aggregate query using a spatial function. The example of that example returns a precision down to tens of millions of millimeters. Now, given this is a database over thousands of kilometers of space, that level of accuracy is ridiculous. It's just garbage. So let's clean it up a bit. Let's do some rounding. Let's round to 1 decimal place. So in this case, I've added a round function around the sum. So I've enclosed my answer here, sum st length geometry. Oh, well, that's not quite. Let's start first. First of all, I'm going to do the length in kilometers, not in meters, because it's a huge number in meters. It's much easier to understand in kilometers. So I'm dividing the length of each river by 1,000 now to get the distance in kilometers, not meters. I am summing the lengths divided by 1,000. So I first divide the lengths by 1,000, then I add all the lengths together, then I do a round function on the summed lengths. Round, or st length, returns a double precision data type. But round accepts a numeric data type. And if you try and plug a double precision number into the round function, it just throws an error. Now, to me, they should include that. That's sort of one of the things that should get labelled up, that they should include double precision in the round function. But for whatever reason, that hasn't been done. So what we need to do is to cast our double precision returned by st length, or in this case, returned by the sum of st length, to a numeric data type with this double colon. So we cast it to a numeric data type, and then after the comma, we put the number of decimal places that we want to display. So now we've got a much better numeric value returned, much more understandable numeric value returned. And this is quite important that you do these kinds of things. These are the things that get you those extra little marks on when you're writing your queries. If you return something nice and neat like this, that gets you marks. If you return ridiculously over precise numbers, you're going to lose some marks. Not many, but you're going to lose a few because it's not the best. It's returning data that's irrelevant. That's just nothing. Okay, area. So we're now doing with the basins, the polygonal barriers. I want the areas of the basins. This is very analogous. There's only one basin for each river in this case, so there's no need to do an aggregate function. One basin. So there's the River Lerma basin, the Rio Balsas basin. These are all individual things. So in this case, we can use the st area geometry function. Oh, I've got a round in there, but I haven't actually implemented it. That's round. Oh, hold on, numeric. No, this is, well, this is actually showing that things don't always work as you perhaps think they do, perhaps. Okay, so I've got the area function, so I get the area of the geometry. That returns the area in meters. The area in meters is even larger than the length in meters because it's squared. So we have to divide by 1,000,000 to get the area in square kilometers. Now in this case, I did try and round it, but I failed. But I didn't get an error. So in this case, I've converted my areas into a numeric, and then I've put the, asked for 1 decimal place, but then I did the division by 1,000,000 afterwards, which has then put all those decimal places back in because of the division function. So what I need to do is to migrate this division function in here, so I need to round the area of the geometry, or what I should think I should do, looking at this, is to take this divide by 1,000,000 and put it in here, so you get the area of the geometry, you divide by 1,000,000, then you put the round function in. But now I'm remembering, a few days ago last week when I did this, you can't actually do this because you can't divide by a 1,000,000 and then cast immediately to a numeric. That causes an error. Hence, I never actually got to finish it, but I imagine with a couple more brackets, we'd work it out and you could get that working without too many trouble. So bear it. So that was some basic functions, simple spatial functions, return some values. PostGIS also supports not only functions, and we'll see some more functions in a minute, but also operators. So this is the equivalent of having an equals or a greater than sign or something like that in a function in a relational query. And this is just from the help function, and it shows you the various syntax for these spatial operations. Now, it's important to note that these spatial operations currently only support bounding box operations. So if we're doing so it's not working on the full geometry of an object, simply on the intersection of the bounding boxes of the object. If you're familiar, you know what I mean by a bounding box, yeah. Okay, so there's a whole variety of these operators. The most common one that's used is the double ampersand, which is a simple intersects operation. So it's the intersection of the bounding boxes of geometries, different geometries. There are also some functions, operators that return distance functions between geometries as well. So we'll see some of these. Let's have a little look at some of these in operation. So if I want to know the intersection, which rivers, now let's read this, which rivers are intersect which basins. So we've got river basins, and then we've got river channels inside them, and we want to know which channels intersect which basins. We can use the double ampersand operator to do this simply on the bounding boxes of the geometries. Why would we want to do it on the bounding boxes of the geometries rather than the geometries themselves? Is that this is really quick. Bounding boxes are really quick to operate on compared with full geometries, which could be really slow. So if you go onto MediWeb interfaces, onto particularly sort of when you're searching data catalogs of the spatial data sets, often those searches are based on bounding boxes because they're much, much quicker than searching the full geometries. So it is actually quite useful with bounding box searches. So we're going to return the river ID, the unique identifier of the river, primary key of the rivers, the river name, the basin ID, identifier, primary key. Something weird going on here, we've got decimals. And the name of the basin that the river segment whether the river segment intersects. So that's our select statement. We're returning them from the river table, which I've given the alias R, just to save me writing river all the time. I just write R, and the basins, which has been given the alias B. And my where clause is just simply where the river geometry intersects, where the bounding box intersects on the basin geometry. So this returns me all the rivers whose bounding boxes intersect with different basins. And we can see that. Why is the basin ID is numeric for when it was imported for whatever reason, and this is probably something where I need to go back and correct this. When I imported the basins were imported as a numeric character rather than an integer, despite the fact that they all stored integers, and I don't know why that is, but that's the reason why we've got a decimal figure in here for an identifier rather than an integer as we have our figure here. This is a lesson. Always check that things have worked as you think they have worked. Otherwise you get somewhere down the line like I did, and you suddenly go, well, why is that numeric? What's gone wrong here? All right, so that's using a function to get an intersect. But it's just on bounding boxes. We'll do non-bounding boxes in a minute. So we'll just see an example of using a distance operator. So what I want to do is I want to calculate the distance. This is the distance of the observations where I've seen each fish species from the center of Mexico City as a latitude and longitude. Remember, my fish data are in Lambert conformal conic, but I have just gone onto the internet and got a lat long in WGS84 for the center of Mexico City. So what I'm returning is an object identifier and the distance. So this is the object identifier is just the identifier of each species that I've observed at a particular location. Or actually my colleagues in Mexico have observed at a particular location. So I want to return the observation number and the distance to Mexico City. So I return, I'm only accessing the fish table, my Gudeade table called G. I want to return the object ID from that table, but I also want to return the distance from Mexico City to that geometry point. So here I use my stgeom from text to create my Mexico City point with an SRID. That's my WGS84 coordinate system. But I need, of course, to transform that into Lambert conformal conic to do my distance calculation. So I can use ST-transform, which calls the Proj4 J library, does the transformation to Lambert conformal conic. There's my 939. Actually, it's a slightly different number from what I showed you earlier. Don't worry about that. It's just another number for the same thing. So I do a transform, call the Proj4 J library, transform it into this coordinate system. Then I can use the distance function here that returns me the distance in meters between the points, my Mexico City point and my fish points. Great. This is just slightly more, this is a more complicated version of a similar thing using distance. So this is what I want to do. I want a table of pairwise distances between my observations. So I've got hollow point observations, and I want to know how far each observation is from each other observation. Yep, in the same table. So I've got one table, point observations. I want to know the distance between the first observation and the second, the first and the third, the first and the fourth, the second and the third, the second and the fourth, the second and the fifth. Well, I can use this operator again. And this is, but I have to have between the 2 points. So I need two versions of the Gudeade, my fish table, to work on. The from points and the to points, so to speak. Distance from here to this point, from there to that one. So I call, and this is an example of what's called a self-join, because you're joining a table onto itself. So Gudeade's G1, so I've got one version of my fish table called G1, one called G2. I am going to exclude from my calculations all instances where the object ID in G1 is the same as object ID in G2. The distance between a point and itself is 0. We're not interested in that. We want to exclude the distance between each point and itself. So that allows us to exclude that. Then I return my first G1 object ID as observation 1, G2 object ID as observation 2, and I use the distance between the first geometry and the second geometry to get my distance. I put that in my function, in my select station function, and that is the distance between the first point and the second point, the first point, the third point, etc. That's quite handy. That's really good. I like that. Nice, simple query. Gives you a pairwise distance table. Spatial relationships. Okay, so the spatial operators only worked on bounding boxes, but as we know, there are spatial overlay involves spatial relationships are much more complex between the different data types. So this is just a slide showing you, hopefully in some of your introductory GIS lectures you've seen this kind of thing, you should be familiar with this. These are the kinds of operators, the spatial operators that need to be implemented. So for example, are 2 points in the same place? Are 2 polygons equal? Are they in the same place, exactly the same? Does a point touch a line? Does a point touch a polygon? Does a line intersect a polygon? These are all the options for spatial relationships between the 3 different vector data types, points, lines, and polygons. And PostGIS supports functions that undertake these queries, exact spatial queries, and what they do is they return either true or false as to whether these criteria are met by 2 geometries, a pair of geometries. So, I want to know whether a river line, which river lines are within which basins. So remember before I did it with a double ampersand, but that was only on the bounding boxes, and I would have got a lot of false results where the bounding boxes happen to intersect, but the line is not actually physically within the polygon. So we would get a lot of false positives. But this we want to do an exact spatial query, and we can do that with the ST within function to find rivers or spatial objects within other spatial objects. So in this case, I'm returning the river ID, the ID from my river. Then I'm going to return each basin. And then I'm going to return whether this river is within, so totally within, the basin, each basin. Okay. So I use if I put ST within RGeom, river geometry, basin geometry, so is the river within the basin, is going to return me a true or false result. Okay? So, river ID 83 is under Laguna, excuse me, I can't pronounce any of these words, Ahorcadas. Basin, no. Is river ID 83 within the Rio Mezquital basin? Yes, true. Is it within the Panoco? False, 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 false. In this case, a line can only ever be within, unless we have basins embedded within basins, which we don't have here, it would only ever return true for one of the polygonal basins. But this is to show that it's returning a true or false value. Something a bit more useful is which basin is each observation within. Okay, so in this case I've got the points and the polygons, and I don't know which polygon each point is in. So I return the object ID, our fish ID. I'm returning the species, and which species it was observed there, and I'm returning the basin that the point observation is within. Now in this case, because I'm doing a query on the basis of the point, I don't want to return true or false for all the basins, I just want to know the Bowles basin which is true, I put my st within in the where statement, so that I only return objects and basins where the point is within the basin. So here we got object, species, basin. A bit more useful. Here's another query. Which species are found within which basins? So instead of saying which observation is within each basins, this is a group query, or this is a sort of group query where we want to know which species are in which basins. So in this case, I can do exactly the same, although we don't have the ID because we're not interested in the ID. We just need species and basins, not the identifier of each observation of each species. And I can use st within basin geometry, and then I simply put in a distinct function to only return the return the unique rows. So I'm returning unique rows of species in basins where the species is within the basin. And I get a list of species and which basins they're found in, which polygons they're found in. Let's switch that around and do it the other way. Well, which basins contain which species? Okay, it's kind of the same thing, but it's ordered round the other way. It's the same query, but instead I'm doing it the other way round. And in this case, I've just done the distinct basins. I've just swapped it round and ordered by basin. Okay, so that's exactly the same thing. But if I want to list it by basins, so if I want species within basins, I do this. So return species and basins. If I want basins with species, page up. So if I want basins with species, I can do it the other way round. So if you're asked to give basins and species, make sure you return them like this and not the other way round. That's another way you get good marks in your assignment, is by returning the fields in sensible orders. Okay. Okay. So that's some examples of some spatial queries. So we want to see the results of our spatial queries, because working in Postgres is all very well and wonderful, but it doesn't exactly give you a great picture of what's actually happening in the geometry. And it's a great idea. I mean, I can't emphasize it more and more that you should always look at your results. Don't write your SQL, then look at it in QGIS and make sure it's actually giving you the result you think it's giving. And we can do that. We can create a view which we can then see in Postgres. Remember, we could see those geometry columns when we loaded up the tables in QGIS. So what I'm going to do in this case is I want to know, I'm creating a view called A Diazi basins, which is the distribution, the basins that contain the species. I think it's Alatoca diazi. As select distinct basin. Remember, this is a sort of just a version of the one we had previously, returning the geometry. Now, what we're returning in this case is we want to turn the basins and their geometry, and then QGIS will access the view, the geometry column in the view, and use that to display it in QGIS. So I've got my fish. Sorry, I've got my fish within my basins. I'm only interested in the species A diazi. I've removed all the others, and I return the unique geometry for each basin and the name of the basin. So I'm returning basins that contain this species, and I'm returning both the name and the geometry as my hexadecimal string. And if I return that, then in here, notice this is a view, so this appears under the views. So we've got the A diazi basins. There's our definition of our query. I simply add PostGIS table to QGIS, it's automatically there because it's all in the system catalogs. It's brilliant. Previously, you had to register the view separately, individually, to get it to be visible in PostGIS. In the new version of PostGIS, you don't. This is wonderful. It picks up the view, and this view is being dynamically created every time you're asking for it. You haven't created a new layer, no new layers created, anything like that, no new tables created. This is just a view, a dynamic view onto the underlying tables. If we change the data if we see a new observation of this species in a different basin, we add that data, the results will change because it's a view that's being dynamically implemented. And I add my view, and these are the purple ones. And just to show that this is true, there's the observations of this species in these couple of basins here. And now we've got the purple, which is the geometry that we've returned from our view. Okay. That's what I've got to tell you about Spatial SQL. Okay, so just as a little bit of summary on here. Remember, GIS are just one type of tool that can access data stored in a spatial relation database. There are many other tools that we might not call GIS that can access that data as well. And we'll, of course, in the second half of the module next year, we'll be building web interfaces onto databases. And those web interfaces could be called GIS or couldn't. Depends whether you like a nice strict definition of GIS or whether you're happy to have a very loose definition of GIS. Spatial database can be used for storage or querying of spatial data. So your spatial data can be stored in PostGIS. You can do spatial processing with Spatial SQL in PostGIS, or you can access your data in PostGIS and in QGIS do your spatial analysis, your overlay in QGIS, and then return the results to Postgres. You've got a choice, depending on what your needs are, your system needs are. You can do your processing in PostGIS, or you can merely use it as a store and do your processing in the externally in the software. And often, if you're doing your processing, your overlay in QGIS, you're actually, remember, accessing the same libraries that PostGIS uses, but you're doing it from a different location. Okay, so analysis does not have to create new data sets. Instead, define alternative views onto data sets. So the hallmark of sort of layer-based, shapefile-based GIS is you're constantly creating new versions of data sets, which is just a nightmare eventually. You end up every step, you create a new shapefile, a new file geodatabase layer. This is incredibly wasteful you have to track these, you have to remember what's been done on each one, what's the lineage that's been used to create this. In Spatial SQL, we can write an SQL question, we create these new geometries, these new features dynamically whenever we need them. We don't need to save them to a database, we can create them dynamically. And it's often quicker and more powerful to create queries and get results in Postgres. Once you know your PostGIS syntax, it's incredibly quick and powerful compared with many graphical user interfaces in ArcGIS. I think it'll be I was wondering whether to do it at some point, but it's a useful exercise to write a sort of grouping query, a grouping and an ordering query, something that groups, something that orders, something that does a spatial join that you can write in about 3 or 4 lines, 5 lines of Spatial SQL. And then if you try and actually look at how many functions you'd have to use in ArcMap to do that, you're talking about one operation probably per line of code if you're lucky. So you've probably done you use 6 different tools in the ArcGIS GUI to perform something that you can write in 6 lines of code in SQL. And of course, if you make a mistake in the GUI, you've got to go back and do it all again. You've got to set all the parameters again. Whereas if you do it In SQL, you just retype your SQL command, edit, run it again. Clearly, there are things like workflow models, like Model Builder, the ArcGIS workflow system that helps remove the repetitiveness of using multiple tools, but it's still, to me, a lot quicker and more powerful to write SQL